Hi, in this lecture I'm going to talk about electric potential energy. So let me first review the basics of energy. So hopefully you remember that the total energy of a system generally consists of two things, the kinetic energy and one or more types of potential energy. And what the types of potential energy is depends on what the relevant interactions are. Right? The relevant forces that determine what's going to happen to your system. Of course, then there's also things like thermal energy, which we get when there's friction, and then the total energy is lost, right? So kinetic energy is turned to thermal energy, for example. But we're not going to be concerned with those cases right now, right? For our purposes, the total energy is going to be conserved, and so kinetic energy can become potential, potential can become kinetic, or some combination of the two. So what's the difference between them? Well, kinetic energy, hopefully you remember, is this energy that's associated with motion, right? So how fast is something moving, and how much mass is moving, half mv squared, right? So if you've got three objects, you work out a half mv squared for each one of them, and that's the total kinetic energy of the system. Potential energy, well, how to calculate it depends on the interaction, right? But generally, potential energy is energy associated with where things are, like the position of the components of the system. Or you might say in more technical terms, the configuration. That is, how are those different pieces that make up your system, how are they positioned relative to each other? For example, some things you might remember, gravitational potential energy on a planet, so in a planet's surface, mgh, h, a position, right? How high are you? And specifically, is it a position relative to the surface of the Earth? Although you can define the 0 point anywhere, but that's beside the point right now. Elastic potential energy, like a spring, right? A spring stores energy. If you squish it, well, if there's a mass at the end of the spring, the energy stored in the spring is a half times k, the spring constant that measures how hard is your spring, how tough is it, and then the stretch or compression distance squared. Right? If you stretch it or you squish it, doesn't matter. X squared is always going to be positive because it's squared. There's energy stored in the spring. If you go out to the, beyond the bounds of a planet's surface, beyond Earth, and you look at planets and stuff in space, still have gravitational potential energy, say Newton's theory of gravity then takes this form here, right? And Newton's theory of gravity says the force is gmm over r squared, while the associated gravitational potential energy is minus gmm over r. So maybe you've met this before in your mechanics course. And of course there could be situations where you've got more than one of them. For example, if you have a ball that lands in a spring and then shoots upwards or down like that, you might have gravitational potential energy and elastic potential energy. But it's always total energy that's conserved. So now we're going to add one more term to this list here, right? And of course a lot of other ones we could have added, but we're going to add a term for electric potential energy. The energy associated with the position of a bunch of charged particles. How are they, what distances are they from each other? What are the charges? How many coulombs? Well, it's going to be a term for the electrical potential energy. So let's make sense of that. So here's the intuitive idea why there's energy stored in a charged particle configuration. So imagine you've got two positively charged particles, plus, right? Now, you're going to hold them in place. You're going to clamp them in place. Just hold them down so they can't move. But they're both positive ones, right? So there's a repelling force between them. This one wants to go to the left, this one wants to go to the right, because they don't like each other. They're the same sign of charge. So let's imagine we then let go. This one's going to start moving left, this one's going to start moving right. And a little bit later, right, sort of like this one is zooming to the left, this one here is zooming to the right. They've gained kinetic energy, right? They each have a velocity now. And is it the same? Well, it depends on what are the charges and more importantly, what are the masses. Is it the same mass for both of them, or do those particles have have different masses. Could be the same, could be different. Let's not make assumptions here. Right, but clearly the kinetic energy here has come from somewhere. It's come from the potential energy held in here. Those two charges, they want to move. Right? As soon as you let go, they'll start moving. The same way, as soon as you let go of a ball you're holding in your hand, it's going to start moving. Right? And it's going to gain speed. It's going to gain kinetic energy. So here we've got potential energy, and then here we've got kinetic energy. And as they're really far away, after a while, the force between them, right, becomes very weak because now they're far apart. So there's sort of a limit of how much total energy they're going to end up with, because eventually they just stop accelerating each other. Well, almost. For practical purposes, the force between them is going to become zero as they're really far away from each other. Similar situation I could imagine is if I start with some positive, well, two negative charges would be the same thing, right? They repel. But let's start with a positive and a negative charge. Let's imagine I have them here. Actually, I want to move them a bit further apart to start off. So I'm going to just draw this again. Put a plus one over here. Put a minus over here, so a bit more space to draw this. Now, those two, they attract positive, negative, right? So for this one wants to go to the right, this one wants to go to the left. I'm holding them in place. Well, there is potential energy associated with this configuration, with them being a certain distance apart. And if I then wait, the positive one, negative one, they're going to move towards each other. They're going to smash into each other. What happens then? Well, it depends on what those particles are, what they're made of, what other interactions might become relevant. If they start out at some angle, like maybe this one is moving downwards, then they might instead start orbiting each other or sort of have a kind of flyby. It depends on the exact setup. But they're definitely gaining kinetic energy when they start out from this position and we let them go. Alright. But hold on. Not all interactions or forces have an associated potential energy. For example, friction doesn't have a potential energy. You could write down that it can make sense of friction, right? When we have friction and we want to deal with energy, we have to calculate the work done by friction. So remember that only forces that are conservative have an associated potential energy. So we're asking, are electrostatic forces, are they conservative? Let's remind ourselves what conservative means. The technical definition is that if I move an object from one place to another, right, and I calculate the work done is the same whether I go in a straight line, whether I go at some sort of path like this, whether I decide I want to go the long way around, right? Doesn't matter what path you take. If the work done due to the force you are worried about, in our case electrostatic forces, if the work done is the same, no matter whether you go from here to here, or from here to here, or from here this way around, well, if the work done is the same, then the work that is to be done as the force goes from here to here is just associated with the initial position and the final position, right? In that case, I can call the work that will get done as the object moves from here down to here, I can call that the potential energy, right? So the same work for all paths. And you might want to review from your mechanics notes the concept of work if you're feeling a bit shaky of what it is and how to calculate it. You might vaguely remember force times distance, but angles are involved too. So, is that true of electrostatic forces? Well, here's a kind of fairly intuitive, not 100% reliable, but fairly reliable way to assess whether a force is conservative, and that is the following. Is the direction of the force on an object, direction is acting, does that direction depend on the path of the object? So, in the case of gravity, it doesn't. Gravity is going to pull you down, no matter whether you go left or right. Friction, on the other hand, depends on which way you're moving. If I'm moving left, friction acts right. If I'm moving right, friction acts left. It always opposes motion, kinetic friction, right? So friction is not conservative. Now, electrostatic forces are actually conservative because the force, electrostatic force on a particle I put somewhere just depends on the direction of the electric field at that point, or if you don't want to include the electric field here in the discussion, you can say it depends on where all other forces are, right? So if I ask what direction is the force on my little particle here, but it depends on where the other forces, the other charges located, or what's the direction of electric field, but it does in no way depend on which way is this thing moving right now. So electrostatic forces are conservative. Note that this characterization is not rigorous. You can come up with exceptions. They're somewhat artificial, involve forces going in circles, but it's kind of a fairly intuitive way to have a good guess. And you could prove it, right? You could prove it by is the work the same method, that indeed Coulomb's law says the electrostatic forces are conservative. And I encourage you to try that. I think the textbook also explains that. So for our purposes, we're going to accept electrostatic forces. They are conservative. So then the question is, what is the potential energy? You write down this question. What is the, am I right, electrostatic potential energy, PE? Right? What's the expression? So how do I figure that one out? Well, the formal way to figure it out would be like I'm going to work out between 2 points, right? What's the work done as I go from here to here? And maybe I can figure it out for a single charge that's sitting somewhere, right? It's attracting or repelling my other charge, or maybe I can figure it out for some collection of charges. But I could work out what is the work done, and that would be the potential energy it had at the start. But we can also do it again in a sort of more intuitive way, and what we have to remember is that the force is the gradient, the downhill gradient of the potential energy. Then I will put my position variable here. I'm going to put r here because I'm going to think about the example of a single second particle to particles interacting. So the distance between them is the configuration variable, the position, right? That's relevant. So here's my one particle, here's my other particle. Call this one Q1, this one Q2. Could be positive, could be negative. So hopefully that is somewhat familiar. Maybe you haven't used it very much. But you can easily check, of course, that is indeed true for something like the spring, right? Differentiate half kx squared, potential energy of a spring, you're going to get minus kx. You put a minus in front, that is the force of a spring. Similarly with gravity, mgh, the h of that, because that's the position variable, well, you're going to get minus mg. That is the weight. It works out, right? So we can kind of inspect, do this by inspection, right? I know what the force is. The force is Coulomb's law, so I'm going to use k q1 q2 over r squared. So that's minus d dr of what, right? Of what? And the what is going to be my potential energy. If you're in more than one dimension, and more than one variable, you'd have to essentially take do the grad operation. But we're not going to worry about that right now. So I want to figure out what do I have to differentiate with respect to the distance between the particles. What sort of expression to end up with this? Now this is fairly simple, so I don't have to explicitly integrate this. I mean, I could, it's straightforward, but I can also just do it by inspection. Well, r squared at the bottom, all the stuff at the top is constant, right? So I just have to increase the power by 1, because when I differentiate it, I decrease the power by 1, so I want to end up there. That means my potential energy is going to be k q1 q2 divided by r, not squared, right? Let's check that actually works out. If I differentiate this, right, with respect to r, I end up with minus kq1 q2 over r squared. Then there's a second minus sign that lives here. I get back the force. Okay, that works out. This is my potential energy for two interacting charges. So electrostatic potential energy for two charges, where r is of course the distance between them. So it looks like Coulomb's law, except there's no squared. And in fact, that is somewhat analogous, right, to an expression you might have met before that I wrote down earlier, the gravitational potential energy, if you're talking about planets, the solar system, and so on, gmm over r, whereas the force was r squared on the bottom. Same thing here, kq1 q2 over r. Notice there's no minus sign, right? But it could be positive or negative because q1 and q2 could be positive or negative. Let's do some examples. Here's my first example. I have two particles. One is plus 3 nanocoulombs of charge, one is plus 5 nanocoulombs of charge, and I imagine putting them 10 centimeters apart. Maybe they're two grains of dust or two little, metal marbles or something like that. I just wrote up here again the expression that we just came to of potential energy. Right? Hopefully you've verified yourself that indeed that gives you back the force when you differentiate it. Another way to write it, of course, is via the 4 pi epsilon naught in the bottom rather than the k at the top. And we know already from studying Gauss's law why epsilon naught is kind of in a sense, the more fundamental constant, but really take your pick. Either way, we want to figure out what is the potential energy associated with the electrostatic interaction of the system. So let's work that out. And really we're just plugging in. I have k times q1 times q2 over r, and I have to make sure I use all the right units. So k is 8.99 times 10 to the 9. I'm going to use 9.0 times 10 to the 9. Then this has to be in coulombs. So this is going to be 3 times 10 to the minus 9 coulombs. Then Q2 is 5 nanocoulombs. That's 5 times 10 to the minus 9 coulombs. And I divide by R in meters, 10 centimeters, 0.1 meter. And I could have had all my units in here, but I know what they are, converted to the standard units. So now we just need to work out what that is. So 3 times 5 is 15, times 9 comes to 135. So when I have this kind of expression with all the powers of 10, always work out just the sort of the numerical values, right? And then deal with the powers of 10 later. And then I have 10 to the 9 to the minus 9, those cancel out. 10 to the minus 9, but then I get 0.1 down here, that's like a factor of 10 at the top, so 10 to the minus 8. And I guess if I want to write this in standard notation, I can point at 1.35 times 10 to the minus 6 joules, right? Because if everything is in standard SI units, you're going to end up with joules. Okay, and we're done, right? That was our first example. So next I want briefly to mention what the graphs look like for those energies. Because remember, potential energy graphs can be very useful to analyze how a system is going to behave, because it provides a very intuitive picture. So on these axes I have energy, on the vertical axis I put a separation between my two particles. I'm still just talking about two particles. But that on the horizontal axis, so this would be r. Notice there's no negative side to this because, well, the particles can't be less than 0 apart. And if they're 0 apart, it means they're in exactly the same spot. Right? This will be in the same spot. And then as r goes big, approaches infinity as I keep going, it really just means they're really far apart, right? Too far for their interaction to matter. So notice that these are all constants, right? I hand you two particles and then I get this bunch of constants, so it's a 1 over r graph. Right? So that would look something like this. right? It keeps getting smaller and smaller and smaller, the energy, as the particles are further apart from each other. But this graph here assumes that the constant is positive, right? That's only if both Q1 and Q2 have the same sign charge. Are they both positive? This whole thing is positive. Are they both negative? This whole thing is positive, right? So either way, this is for plus plus or minus minus. Either way, you're going to get a positive potential energy, 1 over R. If, on the other hand, you have 1 plus 1 minus, and it of course doesn't matter which is which, it's not even a question that makes any sense. If I just have those two terms, because multiplication is commutative, meaning you can swap those two, then I'd get a negative 1. And how steep this thing is, how far down does it go, that depends on the size of charges, right? How many coulombs do I have? I haven't put a scale here, so that overall shape is going to be correct no matter what. This is if I have plus and a minus. So then the whole expression is going to be negative, because one's plus, one's minus. Everything else is positive, so there's 1 minus, this thing is going to be negative. And now we can use the intuition we have with those energy graphs. Remember, the intuition is this. We can sort of imagine, right, you put a marble somewhere on this little track here, and I ask, well, what's the force on it? And it's just like imagine which way is the marble going to roll, and how quickly is it going to accelerate. And you can tell, oh, if they're close together, two positive ones, right, then the marble is going to wants to roll to the right, a lot of acceleration, a lot of downhill force to the right because it's steep. So that makes sense. Two positive charges close together, they want to push each other further right, right? That's the graphical intuition of the fact that force is minus the slope of the potential energy. So hopefully that makes some sense to you. Meanwhile, right, if I have a plus and a minus and I place them, say, a certain fixed distance apart, you can imagine I have a marble here. What's going to happen to it if I just let go? Well, there's a force to the left. The intuition is the marble wants to roll down the hill. It's going to speed up as it does it, as the particles get closer together towards decreasing R. And it's going to actually go infinitely fast once it goes down there. Now, the interesting aspect about this graph here, the plus minus one, is that if I start down here and I can ask how much of a shove do I have to give my particles so they start flying apart, how much initial velocity do I need so they fly apart and don't come back? Well, I have to add enough total kinetic energy to take the total energy above the 0 line, so they would just keep going and never reach a point where they have no kinetic energy left. We just keep going and we fly apart. We'll do a calculation to that effect in just a moment. But again, if you feel, oh, you haven't looked at those energy position graphs in a long time, and maybe you should go back to the textbook or your notes from your mechanics course to make sure you understand how to use them and how to have this intuition about them, right? The marble here, which way is it going to roll? It's exactly what the force associated with this potential energy graph is going to do. Another question you can ask is, well, what about the situation where I have more than just two charges? What if I have 3 or 4 or 10 or 100? Well, let's look at the situation with 3. I imagine I've got 3 balls, 3 objects, and they're charged. They carry some charge, QA, QB, QC. Well, there's a potential energy associated with any interaction, right? So there's an interaction between those two. They're going to attract or repel each other, depending on are they the same sign or are they opposite signs. B and C, they're going to attract or repel each other, and there's an interaction between them, and the sign again depends on are they the same sign charge, are they both positive, both negative, or are they opposites, one's positive, one's negative. And then there's a third interaction between those two. So my total potential energy is just the sum of the potential energies for any one pair. So let's write this out. The sum of the potential energy for each pair. Now, when you have 100 charges, it can become fairly complicated. It's a number of different pairings, right? You can work out what that is. Basic combinatorics. It's a fairly large number, right? Not something you want to do by hand, but maybe you can have a computer to help you if you had 1,000,000 charges, or you can do certain approximation or integration methods. And one way to think about what happens if I add one more charge to some existing charges is via what's called electric potential, not potential energy, just potential, something we're going to come to very soon. But right now, let's look at the situation with the 3 charges. So in this case, I would write potential energy, let me do it as a subscript, A and B, plus the potential energy of B and C, plus the potential energy of A and C. And if I call this distance RAB, RBC, RAC, right, I mean the separations, then I would write this as K, QA, QB over RAB. So just as if C wasn't there, then K, QB, QC over RBC. This is this interaction here that doesn't care about A. And the last one, K, QA, QC over RAC. You work it out. And if those are different signs, say positive, positive, negative, then some of those terms might be positive, some of them might be negative. Well, you've got to keep track of the signs. But you just add them up. Just be careful as you do it. You're going to get some practice doing this in some of your homeworks. So let's work an example where we're actually going to use the conservation of energy from one earlier situation to later situation. And here's the scenario I envision. I imagine I have 2 spheres, a big one and a small one. And they have radius little r, radius big R, capital R, charge Q and mass M, and this one is charge capital Q and just a very large mass. It's very heavy compared to the other one. I'm asking, what is the minimum initial speed that, in this case, a little charge has for the small sphere to hit the large one if starting from far away? Right, so imagine this one is really far away. I'm aiming it at this ball I'm shooting, but I assume they're both positively charged, could be both negative, but same sign, so there's a repulsion force between them. And you can imagine if it approaches too slowly, it'll just get pushed away, turn around, and shoot back off. Because there's a repulsion, because they're both the same sign of charge. But if I shoot it fast enough, right, then yes, it's slowing down on its way, but it's still going to hit. But I want to find the minimum speed I need starting from far away. So let's calculate that using energy conservation. So the 2 points in time I'm comparing is the point in time at the beginning when the balls are really far apart and this thing is just about to start out going at that initial speed that I ultimately want to find. And then the second time is where the ball just hits, right? It just barely hits. So let's get started on that. So I'm going to just put at the start the kinetic energy is 1/2 m v initial squared, right? That's the kinetic energy of this one. We don't know what this is, but we want to find it in the end. And this one is super heavy and it doesn't have any initial velocity and it's not going to gain any either, because we're just assuming it's essentially infinite mass for all practical purposes. So even if these push against each other, this one's not going to budge. So this one, and then I could add the potential energy. Well, the potential energy is going to be K, Q over R, initial. So I don't want to use little r is the radius of the sphere, right? So I'm not just going to write r. It would be misleading, at least, or really wrong if someone might think it's this r, right? But the initial separation, right? Maybe I should annotate this. But for our practical purposes, well, we know we mean the initial separation, and this is infinity. Maybe it's 10 million miles, right? Or just 3 meters, doesn't matter, but it's a very large number. And so that makes this 0. In practice, it would be a tiny number, a finite number over a very, very, very large number. But you know, for practical purposes, this is 0 if it's really far away. Okay, and so this is the beginning. The other ball, as I said, doesn't have any kinetic energy. Then at the end, or at the point of collision, that's the other point of interest. So that's the other point where I'm considering the energy. Right. So let's have a look. At that point, this ball moves all the way over here. I'm just going to sort of pencil it in. Right? It's going to be right there. That's the collision. So, I don't care how slow the ball goes. Right? It might be going and hitting it at a really high speed, but that means it sort of had energy to spare. I want to figure out what's the minimum amount of energy it needs at the beginning, the minimum speed initially. So I am okay with the ball just slowing down and just barely touching. Right? So I'm going to assume there's 0 kinetic energy left. Right? It could be more if it slams into the ball, but because we're considering the minimum case, right? So we consider the minimum case. By the minimum amount of energy, it's okay for it to slow down, to just barely have enough velocity left to just boink, touch it, but just sort of very gently touching it, right? Not slamming into it. If it slams into it, sure, it hit it, but it had more energy than it needed. Now, what's the potential energy? Well, what is the separation between the balls? Okay, Q, the two charges, right? Little q, big Q. Well, it's helpful to have this picture because the separation is not 0. If I put in divide by 0, this would be infinity and I would need infinite speed. Important part is that I have to measure the separation center to center. With, point particles, they'd actually, never be at exactly the same point. With finitely sized spheres, they hit each other and there's still some separation between them, and you can easily see that it's the radius of this one plus the radius of this one, center to center. So that's the distance. They're going to be, their centers are apart. Then we put R plus R down here. Let's make sure you understand this. So once again, from center to center, I go from center to edge, from edge to other center. Little r plus big R, because little r, remember, was the radius of the small ball. Okay, so this one's 0, this one's 0. Okay, it makes my life fairly easy because I'm considering this minimum case. So I can now set those equal, because no energy is lost. Right? There's no friction, no air resistance, nothing of the sort. So I can set those energies equal. And so what am I going to get? I'm going to get that 1/2 mv squared, initial velocity still I'm going to find, is equal to this plus 0, right, is equal to 0 plus this. So k q over r plus r. And so I can find my answer. The initial speed needed is going to be 2k q over r plus r. Don't forget the m, you divide by m. And then this was squared, so I'm going to take the square root. And there we go, that's going to be my answer. Algebraic in this case. Okay, let's study another example. The final example is we're going to calculate the energy needed to ionize a hydrogen atom. So, got to be careful here. We're not actually going to do the proper calculation that will require quantum mechanics, which you're going to be learning in a future course if you stick with physics. So maybe you really should say estimate using essentially the classical, the non-quantum electrostatic forces that we've been learning about. But to do that, even we need a couple of bits of data. So let's visualize the hydrogen atom. There's a proton in the middle. That's the nucleus, a very simple nucleus, the simplest one you can think of. And then there's one electron that is. For now, we're going to visualize this is going in a big circle around it, a bit like a planet around the sun. Yes, it's not accurate. You need to treat this quantum mechanically, but for the purposes of this course, we're going to think of it like this. And actually, our calculation is going to be fairly good with this assumption. So this is a certain distance called r0, and it's circling around at a very high rate. And I invite you to calculate how quickly it moves. We're sort of going to do that anyway, actually. And so this one, there is some initial kinetic energy. This thing is at rest, but this thing is moving. So it has some kinetic energy, but there's also potential energy, right? But because I want to take it further apart, but stretch the distance between them until it's infinitely large, I want to bring it out of this potential well. So if I visualize this with my graph, right, I have the plus-minus graph. This is going to be R. This is going to be the energy. It looks like this. And it starts out somewhere here. This would be my R0. The starting point. There's a certain amount of negative potential energy. But then on top of it, it does start out with some kinetic energy. So its total energy is going to be maybe somewhere there, maybe. Right, so this would be my kinetic energy that I have to add to the potential energy. But overall, it's still negative. So I want to know how much extra energy do I need to add to this thing, right, to take it to the positive energy land. Because if I get it there, that means it can fly away and never run out of energy as it goes further and further and further away from the proton in the middle. So we need some data here. What's the size of a hydrogen atom? So we're going to take the so-called Bohr radius, and that is about 5.3 times 10 to the minus 11 meters. It's called the Bohr radius. And of course, this has a charge E. The proton has a charge E, remember? So I can write this down. Proton. Charge is E. This thing has a charge minus E. Minus the electron. So same charge. The electron also has a mass that we may or may not need. So initially, right, we have a certain amount of potential energy that we can calculate. We also have some initial kinetic energy. So, how are we going to deal with that? We have to calculate how much initial kinetic energy this thing has. Right, so let's get started. Initially, meaning the atom's just sitting there, left to its own devices. Well, the potential energy, the electrostatic potential energy, is K Q1 Q2 over R. In our case, that is K, yes, then E, proton, minus E, electron, right? So again, E squared, divided by R0, that initial radius. But there's also kinetic energy because the electron is moving, right? So 1/2 mass of electron V of electron squared. Okay, how do I deal with that? Well, here's something to note about this motion. It's going in a circle, right? So circular motion. That means mv squared over r. Right, that's the force. What's the force that keeps it in a circle? It's the electrostatic force. Right, circular motion, this is the centripetal force. We know it's going in a circle, so whatever force is doing the pulling, it's got to be equal to this, where this is of course the electron. And what is the force? It's the electrostatic force. K Q1 Q2 was E squared divided by R naught here, R naught squared, right? So centripetal, this is the centripetal force expression. What force is the centripetal force? Oh, it's Coulomb's law, right? With charges E and E. The minus sign, well, that tells it's attractive, right? But the magnitude of this is equal to this. So I can use this trick then, in a sense, right, to replace my expression in the kinetic energy. I can cancel out this with this, like one of those 1 over R naught is going to cancel. And so I can just rewrite that as 1/2 times this thing here, K E squared over R naught. And what you notice, curiously, right, the kinetic energy is opposite sign of the potential energy. It has a minus sign here. And has a half here, but no half here, but it's the same expression. And that's a special case of what's called the virial theorem, which applies to essentially central forces pointing towards a point somewhere in the middle. There's a certain theorem that relates potential energy to kinetic energy. Broadly speaking, this 1/2 of this, so kinetic energy is half of the potential energy, except for minus sign. That is one particular instance of the so-called virial theorem, if you want to look it up. I'm going to write CF, compare with Konferatur, the virial theorem. So you'll probably find some fairly technical descriptions if you just Google this online. Alright, but now, for our purposes, we have the initial potential, initial kinetic, so the initial total is equal to, well, minus Ke squared over R naught. We know what all those values are, right? This is the Bohr radius, this is the electron charge, 1.6 times 10 to the minus 19 coulombs. This is K, and then we're going to add to it the kinetic energy, 1/2 Ke squared over R naught, and that of course just comes nicely to minus 1/2 Ke squared over R naught. So on my graph, really the way I should have drawn is that the kinetic energy takes exactly halfway up to the total zero energy line that we want to get to in order to make it out. Okay, so now this is our initial energy as the electron goes round and round and round. Now we imagine we're going to shoot probably a photon at it, a particle of light, right? So like this, here comes the photon. In physics, we often write little gamma for photon, especially in the context of like field theory, but I'm just going to do it like this. So you've seen it. Notation here doesn't actually matter. In some way, we are going to add energy to the system, right? And probably we're shining light on it. So we hit it with a photon, bang, it has a lot of extra energy. Well, how much energy do we need? What's the final energy when it's ionized? Ionized means the electron has left the proton, it's somewhere far away, it's a little lonely proton left all by itself. So in that case, the potential energy is going to be pretty much the same we had for the two spheres at the beginning, Ke squared, well, E squared, the amount of them is minus, divided by infinity. And I know, mathematicians, this is not correct, but you know what I mean here. This is 0. Should just write over R as R becomes infinity. The kinetic energy at the end, well, the electron could have some left. If the photon was very energetic, it sends this one off to increasing R. It might always have some kinetic energy left, move really fast, even when it's already really far away. But the minimum energy needed is just enough to make the electron fly away. And as it flies away, it slows down, but it never quite comes to a stop. So it keeps going, right? So that's why we want to get to have enough energy to essentially just make it to like up to this line here, the arrow I drew here, just barely up to this line, maybe a teeny bit above it, but you know, mathematically just up to this line. Total energy 0. I'm okay with the electron not having any kinetic energy left once it's really far away. So final total energy 0. So I have this one at the beginning, I have this one at the end. So how much energy do we need to add? Well, we need to add exactly the positive of this. Need to add plus 1/2 k e squared over r naught. Right? Because then I have this much, and I add to it this much, and I end up with 0. Hooray, we've ionized the hydrogen atom. So now I just plug in. You plug in all the values. 9 times 10 to the 9, 1.6 times 10 to the minus 19 squared, divide by 5.3 times 10 to the minus 11. Make sure you actually do this. Make sure you do it carefully. But I think the answer you're going to get to is 2.3 times 10 to the minus 18 joules. And another way to write this in different units that we're going to meet very shortly is so-called electron volts, and this is about 14.35 electron volts. Electron volt essentially having sort of replacing a coulomb with a, it's taking a joule and dividing it by the number of electrons in 1 coulomb. It's sort of like electron volt to a joule is what an electron charges to a coulomb. We'll come back to this. Now, is that true? Is it accurate? Well, if I do the calculation quantum mechanically, or I measure it in the lab, the actual value, calculate carefully with all the quantum mechanics that you don't yet know, is 2.18 times 10 to the minus 18 joules, or very famously 13.6 electron volts. So we're not exactly there. Our calculation involving just the classical physics, forces, energy, electrostatic interactions, isn't exact because we didn't take into account the fact that really we should be doing the calculation using quantum mechanics. But we actually got really close, you know, within like 5% or so of the actual value. Alright, thank you for watching. This was our introduction to electrostatic potential energy with some examples. We're now going to move on to the next topic, which is electrostatic potential. And potential is to potential energy a little bit like electric field is to electrostatic force. So I'll see you in the next video.